Hi guys, today we're going to measure the evaporation of some liquids. I know, it sounds boring and you might be wondering, why would we even want to do that? Why? Because the rate at which something evaporates is dependent on a couple of factors. Number one, its molecular weight, and number two, the type of intermolecular force that it exhibits. Intermolecular forces are the forces of attraction that occur between molecules. Some molecules have very strong intermolecular forces, and some molecules have very weak intermolecular forces. And those forces depend on a couple of factors. Number one, how big the molecule is, how many electrons it has floating around inside the molecule, and also the shape of the molecule and whether or not it's polar or nonpolar. Nonpolar molecules, like this pentane here, have typically pretty weak intermolecular forces that are really only dependent on the motion of electrons all throughout the molecules. As those electrons zoom around inside the molecule, sometimes they become unbalanced and create sort of a more negative end and a more positive end. And that can then help attract to the neighboring molecules who are doing the same thing. This type of interaction is called London dispersion force, and it's typically the weakest of the intermolecular forces. However, if the molecule gets bigger and bigger and bigger and has more and more electrons, the London dispersion force can get quite strong. Other molecules, like this sulfur hexafluoride, for example, have more of an asymmetrical structure and maybe even a lone pair sticking out on one side. And so it has an uneven distribution of electrons, a more negative end and a positive end, or a dipole, and it can then attract to a neighboring molecule with its dipole. This is actually called the dipole-dipole force, and typically it's a little bit stronger than a London dispersion force. And finally, some molecules are so polar that they actually have a dipole-dipole force that is strong enough to get its own category, and this is called hydrogen bonding. Hydrogen bonding occurs in molecules that contain hydrogen bonded to nitrogen, oxygen, or fluorine. Oxygen, nitrogen, and fluorine are very electronegative, and they create very polar bonds with those hydrogens, and that results in a very strong intermolecular force. Molecules that exhibit hydrogen bonding might include ammonia, with the nitrogen attached to 3 hydrogens, or alcohols, in the case of this N-propanol, with an OH on the end. And we always go on and on about how water is so amazing, and one of the reasons that it is so amazing is that it has 2 OH bonds, so it can do a lot of hydrogen bonding. Evaporation is the process in which a molecule leaves its neighbors in the liquid state and enters the vapor state above it. So it might make sense that the stronger the intermolecular force holding those molecules together, the less evaporation you're going to have. It might also make sense that the molecules that are evaporating have a larger kinetic energy than those in the liquid below. And so as they evaporate, they take energy with them, and the result is that the liquid below gets cooled and the temperature drops. And we're going to measure that change using our handy dandy little probes here and see how much the temperature drops when different liquids evaporate. Let's start with ethanol and propanol. Both of these are alcohols and they have the OH on the end. The only difference is that the ethanol only has 2 carbons and the propanol has 3 carbons. So I've got these temperature probes with a little bit of filter paper attached. The first one, channel 1, is in ethanol. The second one, channel 2, is in propanol. And you can see over here they're connected to my Vernier LabQuest, and you can see their starting temperatures right there. Next, we'll hit start, and we'll start collecting data. Give it a second to give us our baseline. And then what I'm going to do is take them out and set them to the side off of the countertop. And I'll get a little tape on there to hold it steady. And I'll do the same with the propanol right next door. And I'll tape that one on as well. I can see here that the temperatures are starting to drop a little bit, and we're just going to let it go and see how far they drop. So after 600 seconds, you can see the ethanol's data here in red and the propanol's data here in blue. So we find that ethanol has a greater temperature drop than the propanol. And now we're going to repeat the same process, this time with butanol. It's got 4 carbons instead of 2 or 3, and pentane, which is a molecule with 5 carbons and 12 hydrogens. So our butanol and pentane have been evaporating for a couple of minutes now. And if we head over to our screen, we can see the red data, which is the butanol, dropping slowly, whereas the blue data, which is the pentane, dropped significantly and now is on its way back up as evaporation is almost finished. And here we are after 600 seconds. Once again, the red data is the 1-butanol, and the blue data is the N-pentane. And let's do it one last time with the simplest alcohol, methanol, and hexane, which is just like pentane except it has an extra carbon on the end. Our methanol and hexane are now evaporating, and if we head over here, we can see that they're in a tight race to see who can get the lowest temperature. And after 600 seconds, we have this data where the red curve is the methanol and the blue curve is the hexane. So there you have it. Things evaporating at different rates and going to different temperatures because they have different intermolecular forces. Bye.